Okay, so this is a question on viscosity and Stokes law. And Stokes law is all to do with when objects, small objects, are flowing slowly. So it's small and spherical, smooth, spherical objects, and the idea they're going slowly, moving slowly. You can use Stokes' law to approximate the drag forces. And so the drag forces, I'll call them DF, drag forces, are given by this formula, 6 pi times the coefficient of viscosity times the radius of the thing and the terminal velocity that it's travelling at. Okay, so we've got an experiment now to determine the viscosity of a sample of oil. So we've got oil in here, we've got a sphere falling through this oil. Now, they are trying to measure the terminal velocity of the sphere using obviously distance and time, distance s and time t. 2 rubber bands were placed there and there. When the sphere passed the top band, a timer was started. The time was stopped when the sphere passed the bottom band. So yeah, we're going to travel that distance in a certain time, and we're going to be able to calculate the velocity, and we'll be able to do that. V equals S over T. Explain why the top rubber band should be placed a short distance below the surface of the oil. Well, this is really because it takes some time. It doesn't immediately hit terminal velocity. So the sphere takes a small amount of time to achieve, if you like, terminal velocity. Achieve the terminal velocity. Right. So, so if you start timing before it's reached terminal velocity, you're not going to get a true value. Okay. So, since terminal velocity takes some time to be reached, timing starts a reasonable distance below surface of oil. Right. Another student suggested using an additional rubber band halfway between the top and bottom rubber bands. This is a very good idea, because if you have another rubber band there, you can measure time 1 and you can measure time 2, or the whole time. And what you can do is you can compare the velocity in this region and the velocity in this region. And if the velocities are different, then it was obviously not travelling at terminal velocity before. Okay, so third rubber band to ensure the velocity is constant, or to check, really. Check is a better word, because you can't really ensure that. To check the velocity is constant, you can measure V1 and V2 in diagram. If V1 is not equal to V2, then terminal velocity is not reached. And it might mean that the second velocity is the terminal velocity. It might mean that. It also might not. You might just have to do the experiment again. So the student used the following equation to determine the viscosity of the oil. Right, so where we've got a bunch of things. So this is, I'm going to write it out a bit more clearly, 4/3 pi r cubed times the density of the sphere times g. And this is equal to 4/3 pi r cubed times the density of the oil times g. And then the third thing is the Stokes law bit, 6 pi times radius times the viscosity times the terminal velocity. Which quantity is represented by this first one? So the one with the density of the sphere in, well, we've got the density of the sphere. This is the volume of the sphere. So all of this lot is equal to the mass of the sphere times the acceleration due to gravity. So this is the weight of a sphere. What quantity is represented by this next one, the blue one, if you like, this one, I should have kept the colours the same anyway. So the blue one is, actually it's almost the same because it's the same volume, but the density is different. This is the density of the oil. So this is the weight of the oil that the sphere displaces. So if you imagine this is oil and you've got a sphere in it. Now the sphere's volume, as it falls, has actually kicked out an equal volume. Let's say this is the oil. There's a little bit less oil, equal exactly how much? Equal to the volume of the sphere that's been pushed out of the way, because the sphere is there. So the upthrust is actually equal to the weight of the fluid displaced, which is this factor. And then the final thing in here, oh no, we don't have to do the final thing. Yes, we do, the quantity represented by this. This is the drag force. And this one is the upthrust from weight of oil displaced. And this dude is just the weight of the sphere. We've done that already. If you like, I can copy that, paste it in here. There you go, nice. Okay, let's see what's going on. The accepted value for the viscosity of the oil used in this experiment is 41 millipascal seconds at 24 degrees Celsius. The student obtained a value which is a bit less than this. So lower viscosity than expected. It could be because maybe the temperature was higher. You know, liquids tend to get more runny when the temperature goes up. So maybe the temperature is higher. That's probably the easiest reason. The other thing is the student could have had errors in the experiment. So what errors in the experiment would lead to a lower value of the viscosity? Well, if you look at the equation, let's say he's finding the force is 6 pi viscosity times R times V. If the viscosity, this is the force, so the viscosity times the velocity is going to be equal to the force. Well, there's a few other factors in there as well. But if the viscosity is lower than expected, it could mean that the velocity was higher than expected. So you might have measured velocity incorrectly. Incorrectly measured. He might have had the velocity too high. And he might have had the velocity too high because the time was too short. Maybe he started the timer late. Late leads to less time, leads to higher velocity than true one. True value. Right, and that's that.